Hi Bobcats! In this video we're going to set up some of the background information that we will use to write names and formulas for binary ionic compounds. Ionic means that it's composed of a metal and a nonmetal. Eventually we will roll polyatomic ions into this mess as well, but here for our first run we're just going to focus on binary compounds, so they only have two elements, a metal and a nonmetal. Ionic bonding results in these extended three-dimensional structures. They get represented lots of different ways. For instance, sodium chloride might be represented this way. The purples represent the positive sodium ions, the greens are the negative chloride ions. But in reality, sodium chloride has many, many more ions all clustered together making a crystal, so the structure might look something like this bottom one. But even that's not a good representation. Either one of these is like showing a drop of water to try to represent an ocean. The ocean is so much bigger. Even the tiniest crystal of sodium chloride that you can see has so many more ions in it than what we can represent here. So, for instance, this one over here shows something like, I'm going to guess this is showing something like 14 sodiums and 14 chlorides. So if we've got all of these different ways of representing sodium chloride, how do we know which one to use? Well, we are going to go with something called the empirical formula, right? Like this one, holy cow, this one has a whole bunch of ions in it, even more. It's got maybe 172 sodiums and 172 chlorides. So when we go to write its formula, we are going to show the smallest whole number ratio between the metal and the nonmetal ions. Right, that smallest whole number ratio, we are always going to use that smallest whole number ratio for ionic compounds. That's what we mean by an empirical formula. We always use empiricals for ionics. And we'll talk about a formula unit. A formula unit is the cluster of ions that is represented in this empirical formula, that smallest whole number ratio between cations and anions. Now I want to step backwards one slide briefly to compare and contrast this with molecular or covalent compounds. Oh, because I'm doing a recording, it won't let me go backwards. In molecular compounds made up of a nonmetal plus a nonmetal, we tend to write formulas that reflect exactly what is present in one molecule. So I believe it was a compound called benzene. On the previous slide, we would say that the formula for benzene is C6H6. We would not reduce that ratio. With molecular compounds, the rules are different. With ionic compounds, we always use that smallest whole number ratio and reduce. So here's a little bit of practice reducing these to an empirical formula. When we're going through the procedure to write the formulas of ionic compounds from their names, sometimes we end up in situations that look like this list of formulas, and most of these are going to be wrong because they are not empirical formulas. So you need to be able to recognize, oh wait, this can be reduced, and then go ahead and reduce it to the empirical formula. For instance, the very first one, Fe2O2. Both of those subscripts can be divided by 2, so we want to do that. We want to go ahead and divide those subscripts by 2. That's going to give us FeO. Now I want you to pause this video for a moment and work through the remaining 3. So go ahead and pause it. Great. Now that you've paused it and you've tried these 3, I want to go through and work them out with you. So this next one, Cr2O6, both of those subscripts can also be divided by 2. That leaves us with CrO3. The next one, Ti2O4, those can be divided by 2 as well, which would give us TiO2. Now, it's not always going to be the number 2 that you're dividing through by, because I picked oxygen. That kind of follows having oxygens. You'll often end up dividing by 2 when oxygen is involved. But not always. Fe2O3, we can't reduce this any farther, so this one is already this one is already an empirical formula, or it's already reduced. We can't reduce the 2 and the 3 any further. Okay, another background piece that we're going to need is certain elements always have the same charge when they form ions. Now remember that ion just means that the species has a charge associated with it. This charge comes from an imbalance in its protons and electrons. Protons have a positive charge, electrons have a negative charge. If the number of protons matches the number of electrons, there's no charge and it's a neutral atom. But if we end up with more electrons than protons, we have more negative charges than positives, and so we get an ion that has a negative charge. We call those anions. If we have fewer electrons than protons, we have more positive than negative charges, and we end up with a positive charge overall on the ion. That happens with metals, and we call those cations. There are a small number of elements that we can make a prediction about their charge simply based on where they are in the periodic table. Now, for these purposes, I want to cross out hydrogen over here on the right. We want to think of hydrogen just being over on the left in group 1. And the elements that are fixed charge are the ones that I've shaded in purple on this periodic table. The ones that are in group 1 will take a charge of 1+. The ones that are in group 2 will take a charge of 2+. And then there are 4 other metals that will make positive charges. They are the ones listed over here, sort of in the middle of the table, shading a bit to the right. Silver will get a charge of 1+. Zinc and cadmium get charges of 2+, and aluminum gets charges of 3+. Now, for the positive ones, the metals, you can look at the last digit of the group number that these elements are in to get their charges. So aluminum's in group 13, it goes 3+. Beryllium is up there at the top of group 2, it goes 2+. Whatever the last digit of that group number is, that will tell you its charge as a positive. That's great for metals. Non-metals, it's a little bit of a different story. If we start with the noble gases are really stable. They're not going to want to gain or lose electrons, so I'm going to give them a charge of 0. Then if we move over to the halogens, they're going to have a charge of 1-. The chalcogens will have a charge of 2-. The nitrogen family, go away. The nitrogen family will have a charge of 3-, and the carbon family, actually just carbon, can have a charge of 4-. These negative charges only apply to the nonmetals. Please don't look at something like lead, which is down in the bottom of the carbon family, and say that that'll be 4-. Lead is a metal. Metals are always positive, so that 4- only applies to carbon. These negative charges only apply to the elements that are shaded in purple. Just real quick summary, group 1 and group 2 are 1+ and 2+. Then these 4 other, I often refer to them as the weirdos or the oddballs. These 4 other metals that are in purple here, their charges are the last digits of their group numbers. And then the nonmetals, the halogens are -1 or 1-. The chalcogens are 2-. The nitrogen family is 3-, and carbon's 4-. And vocabulary word, the metals are positive, they make cations. The nonmetals are negative, they make anions. When we go to name these, the cations, we're going to name them just by their element names. So if we've got Al3+, it's aluminum. If we have sodium+, we just call that sodium. If we're talking about the sodium all by itself, we often just throw the word ion on the end of that. The anions, on the other hand, and they're going to be the second ones in the formulas, they get their ending changed to IDE. So something like sulfur with a 2- charge becomes the sulfide ion. Chlorine with a 1- charge is known as the chloride ion. So real quick practice with these. Please pause the video and try these yourselves. Once you've done that, come back and restart the video. All right, now that you've given that a shot, zinc is one of our fixed charged ions. It's one of those 4 weirdos over in the corner of the transition metals. Zinc is in group 12, so zinc will go 2+, and we just name it zinc, or the zinc ion. F, that's fluorine, that's a halogen. The halogens all take a 1 negative charge, and we change the ending of the negative ones to IDE, so this becomes fluoride. N is in group number 15. Everybody in that nitrogen family that goes negative, the nonmetals, end up with a 3- charge, and we're going to call this nitride. We're going to, again, change the ending to IDE. And last but not least, calcium is in group 2, and so it's going to have a 2 positive charge, and we're just going to call it the calcium ion. The positive ones, we leave the names alone. The negative ones, we put IDE. That also corresponds to their position in the name or the formula. The positive ones are first, the negative ones are second. So just like with covalent nomenclature, we leave the name of the first one alone. We change the ending of the second one to IDE. All right, so that takes care of all of the elements that are shaded purple. What about the rest of them, right? That's most of them. What are we going to do with the rest of them? Well, we're going to need Roman numerals as part of their names. So I'm going to real quickly recap the Roman numerals. 1 is the letter I, and 5 is the letter V. If we're going to make the rest of these, we're just going to combine I's and V's. If we put 2 I's side by side, we add them up and we get 2. We follow that same pattern for 3. We just put 3 I's right next to each other. For 4, we're going to bring in the number 5, and we're going to take 1 away from it by putting a 1 in front of it. For 6, we're going to take the number 5 and put a 1 after it, meaning that we add the 1 to the 5 to get 6, and we'll follow that same pattern for 7. We're going to do a VII for 7. For Ionic nomenclature, you need the Roman numerals 1 through 7, so if you aren't familiar with those, make sure you get those under your belt. For naming all of the other metals in the periodic table, we're going to take whatever the charge is and write that charge after the name as a Roman numeral in parentheses. So iron commonly occurs as either an ion with 3 positive charges or with 2 positive charges. So when it has 3, we're going to call it iron and then open parentheses, Roman numeral 3, close parentheses. When we read that out loud, we just say iron 3. For iron with a 2 positive charge, we're going to name it iron 2. And again, that Roman numeral 2 is in parentheses when we write it, but when we say it, we just say iron 2. Just real quick practice here. Pause your video and try this yourself. I'm running out of time, so I'm just going to say this first one is manganese 7. If you haven't tried these yourself, please pause and try them yourself. Ti4+ is going to be titanium 4. Ag+, this is a trick. This is just silver. It is fixed charge. For all of the fixed charge ones, we don't use the Roman numerals. Chromium 6 would be Cr6+, and copper 2 would be Cu1+. It is also fine for the positive ones and the negative ones to not write the number, to just write the sign.